Okay, ECO311. Now we move on to chapter 7. So we officially begin with multivariate regression analysis, meaning the regression contains at least two explanatory variables. Okay, and then for slide number 3, I think in reality it is hard to run bivariate regression because it is highly unlikely to have only one explanatory variable that could explain the variation of the y value. So I have an example here. With regard to factors affecting students' academic performance, it is impossible for study hours to be the only explanatory variable influencing students' academic performance. So it makes more sense to run this regression as a multivariate regression. In other words, study hours along with party hours, lecture attendance, tutorial attendance, and so forth, even maybe parents' education, part-time work status, part-time work hours, or even whether the student owns his or her own laptop could also play an important role to explain the student's academic performance. Okay, so I have an example here, multivariate regression. So this is the e-views output. So marks is your y or y hat, sample size is 30. And then B1 hat is my constant, B2 hat is this slope parameter on study hours, 6.3661, and this is my first explanatory variable x2, study hours, and then B3 hat is my party hours parameter minus, I think it makes more sense for the negative relationship between party hours and marks, so you have a negative slope parameter, 0.1706. So in other words, in the multivariate regression, you have two slope parameters, B2 hat in connection with the study hours x2 variable, and B3 hat minus 0.1706 in connection with the party hours x3 explanatory variable. And then R square, adjusted R square, you are going to learn later. And then these are the standard errors of each parameter. So this is standard error of B1 hat, standard error of B2 hat, standard error of B3 hat. Degrees of freedoms, the equation remains the same, n minus k. But now since we move on with multivariate regression, k is no longer 2. Remember, k is always equal to 2 for bivariate regression. So in this example, k will be equal to 3 because you have got 3 parameters, 1 constant and 2 slope parameters. So 3 parameters in total. And then the next part has to do with the interpretation, and then the important thing is to talk about the ceteris paribus conditions. Okay, so let's start with the constant. B1 hat 5.4476. It actually means what happens to your y hat when all your x's, x2 and x3, they are both equal to 0. So let's look at the interpretation. It means if someone spends 0 time to study, meaning x2 equals 0, and 0 hours on partying. So meaning x3 equals to 0. So in other words, I repeat, it means when x2 equals 0 and x3 equals 0, the sample regression function predicts that on average, y hat, the final mark, equals 5.4476. And there's no reason to celebrate because it means failure. It's much lower than 50 marks actually. Then the student actually failed. P2 hat, my first slope parameter, P2 hat, 6.3661 in connection with x2 study hours. So let's look at the interpretation. It means when x2 study hour increases by 1 unit, the sample regression function predicts that on average, final mark would increase by 6.3661, and now he is the ceteris paribus condition, providing there is no change in the other explanatory variable, x3 party hours. So keep this ceteris paribus part in mind. You must mention this in the if I really ask you a question on how to interpret each multivariate regression slope parameter, and I don't accept the answer ceteris paribus, you have to give me the full explanation, which means the sentence, providing there's no change in party hours. And then let's interpret the last slope parameter, B3 hat minus 0.1706. So it means if x3 party hour increases by 1 unit or 1 hour, the sample regression function predicts that on average, final mark would decrease, see the negative slope parameter, decrease by 0.1706 units or marks, and then the ceteris paribus condition, providing there is no change in your x2 study hours. And then the interesting case is, I'm not going to go that far, but just for your interest sake, what if both x2 and x3 increase by 1 at the same time? Then all you have to do is just to add the two slope. parameters together. So just for your interest sake, I repeat, I'm not going to ask question on that. It is too much for third-year student, but it's good for knowledge enrichment purpose. So if someone increases his study hour by 1 and also party hours by 1, it means x2 and x3 both increase by 1 unit at the same time. The sample regression function predicts that on average, final mark would increase by 6.1955, which is the sum of B2 hat and B3 hat. And then for the partial regression parameter, it is not prescribed, so we can skip these few slides. And then these multivariate regression parameters, same old story actually, except again for multivariate regression, k is no longer equal to 2. So if I refer back to the previous example, then k is equal to 3. But you must interpret the regression equation carefully just to find out how many parameters there are in total. And then the same old statistical properties of multivariate regression, just like the bivariate regression. So let me pause for 30 seconds here. Okay. And then R square for multivariate regression, it is still the same equation, explain sum of square divided by total sum of square. And the definition of R square remains the same, proportion of variation in Y explained by the variation in, this time, all explanatory variables jointly. Remember, we move on with multivariate regression. And again, as I mentioned in the last lecture, the recap lecture, for multivariate regression, the square root of R square doesn't really mean anything, but only for bivariate regression that the square root of R square gives you the correlation coefficient between X and Y. And then there is one weird characteristic of R square. One weird characteristic of R square is that as long as you add more and more explanatory variables, your R square is guaranteed to increase, regardless of whether these additional explanatory variables are relevant or irrelevant. Then it would become a bit problematic if you want to compare the goodness of fit or R square of two regressions with different numbers of parameters. This is why we move on to rather use adjusted R square to compare two regressions, or the goodness of fit of two regressions with different numbers of k and even the sample size. So this is the equation, adjusted R square with the bar, it is equal to 1 minus bracket 1 minus R square, and then bracket n minus 1 divided by n minus k. You can see the equation of adjusted R square. You see n and k featured. Then it means adjusted R square already considered the differences of n and k between the two regressions. But one reminder, if you want to compare the adjusted R square of two regressions, for the two regressions, the y must be in the same form. For example, they are both linear in this example. If you look at the first two regressions here. Okay, so let's look at the following examples on the slide. So I've got three regressions, different sample size, different k. And if we use theoretical thinking, let's look at the first regression, marks explained by study hours and party hours. I think both explanatory variables make sense. I think it is a good regression. But if we look at the second regression, marks explained by study hours, party hours, and work hours, I think we should add the work hours because some students work part-time. It could have some negative impact on the academic performance. So I think regression 2 is actually better than regression 1 because it includes one more relevant explanatory variable. But the third regression, I think it commits overfitting, meaning including an irrelevant explanatory variables, because I don't think puppy size has any influence on your academic performance. So if I use my theoretical thinking, I will rank the three regressions in the following order. Regression 2 is the best, followed by regression 1, and then regression 3. But if we use R square as an indicator to compare the three regressions, remember the weird characteristics of R square that I mentioned previously. As long as you add more explanatory variables, R square is guaranteed to increase. So in other words, the R square of the first regression must be the lowest because it has the lowest number of explanatory variables. So if we use R square to compare the three regressions, we somehow reach a conclusion that regression 3 is the best one, because it has the highest R square, followed by regression 2 and then regression 1. But remember from the previous slide, we already talked about that. If n and k are different amongst the regressions, R square is the wrong indicator for comparing the goodness of fit. Strictly speaking, we should rather use adjusted R square. Okay. And then luckily, all three regressions for the y variable, they are of the same form, in linear form, so it is possible to move on to use adjusted R square to compare the goodness of fit of the three regressions. And then this slide shows the calculation of adjusted R square of each regression. So let me just go through the first one. Adjusted R square of the first regression equals 1 minus bracket 1 minus the R square 0.8975 bracket n minus 1, n is 25 minus 1 divided by n minus k, 25 minus 3. So this is how you derive the adjusted R square of the first regression. Let me stop for 30 seconds and see if you can understand the adjusted R square calculation of regressions 2 and 3. Okay, so upon interpreting the adjusted R square answer, don't you notice that adjusted R square is the highest in regression 2, followed by regression 1, and then regression 3 has the lowest adjusted R square. Then don't you think the results from adjusted R square conform with theoretical thinking that indeed regression 2 is the best one, followed by regression 1 and regression 3, which commits overfitting, including the irrelevant puppy size explanatory variable, is actually the worst one. So let's look at the second example, slide number 15. First regression, consumption explained by income and household size. It makes sense. Second regression, I think it commits overfitting because it includes an irrelevant explanatory variable, size of the bathtub. Okay, and then the third regression, theoretically speaking, is the worst one because size of the bathtub and number of times the person got the voice should both be irrelevant, actually. So theoretically speaking, regression 1 is the best one, followed by regression 2, and finally regression 3. But using the wrong indicator, R square is guaranteed to be the highest for regression 3 because it has got the highest number of explanatory variables, followed by regression 2 and regression 1. But this is, remember again, R square is the wrong indicator to compare goodness of fit of regressions if n and k are different. I think in this case, it is the k that is different. And then let me stop for 30 seconds to see if you understand the adjusted R square calculations of each regression. Okay, so at the end, adjusted R square is the highest in the first regression, followed by second regression, and finally the third regression is the worst one. Then don't you notice that the conclusion derived by using adjusted R square conforms with economic theoretical thinking? Okay. And then in session 7.10, there is a short session on polynomial regression models. This is an economic example. It means y as a function of x and x squared, actually, or even x cubed, if there is more than one turning point in the graph. Okay, but it is actually already covered in chapter 6, so that is no longer the focus for ECO311. But just a reminder, you can at least go through session 7.10. And then session 7.11 is just for knowledge enrichment purpose. So that's it for this chapter. So we are progressing well. And then for chapter 8, we would once again conduct the confidence interval hypothesis testing type questions, but for multivariate regressions. So expect a lot of calculations and the use of the distribution table for the next chapter, chapter 8. Okay, thank you.